So let's talk through maybe one other concept that is helpful in going through this to set up like a heat transfer problem, and then we'll hopefully have a few minutes for an example. Okay, so let's talk about this idea of a space resistance. And let's see, what I want to do is let's maybe start with, let's start with our equation for Q dot I to J. So the heat transfer from surface I to surface J. And we wrote that as this equation, which was AI Fij times, times sigma times the quantity Ti to the fourth minus Tj to the fourth. Sorry, let me just do something here. Okay, erase, my bad. Qi to j, I skipped half a step and it's going to mess me up. So let's do this the right way. Qi to j is this. It is Fij sigma area I Ti to the fourth minus Fji area j sigma Tj to the fourth. Right? That's our energy balance Qi to j. What we want to do is maybe write this in a way that looks more like a potential, more like our sort of typical way of writing heat transfer equations, which is some driving potential times some, or divided by some resistance. So if you remember back to last lecture, we discussed this idea of emissive power, right? Where sigma T to the fourth is the emissive power. So we can rewrite this in terms of the emissive powers by saying that Q dot I to J is equal to the area of I times F I to J times the emissive power EBI minus EBJ. So also, okay, what just happened with this view factor? So this Fji remember that's equal to Fij AI. So just make that substitution and pull it out. So it's just AI Fij. And then EB, the black body emissive power, is sigma T to the fourth. So we've just rewritten it this way. This should look like the thing we're accustomed to working with, except instead of a temperature as our driving potential, we have an emissive power as our driving potential. So we can rewrite this and say, okay, this is actually something like Q dot Ij is equal to EBI minus EBJ divided by some resistance. In this case, the resistance is not quite like what we're used. It's not like heat transfer coefficient times area. It's a non-dimensional number, a fraction from 0 to 1 times an area. So actually the units on this are a little different from typical resistances, which is why we call it, say, a space resistance, or I will also call it a geometric resistance. And I'll call it geometric resistance because we're going to use the nomenclature Rg for this resistance because it has different units. Right, the units on this resistance are should be 1 over meter squared. So this resistance is basically telling you how hard is it for a photon to get from surface I to surface J through space, through this vacuum in space. But it's another way of writing this. So if we have this idea of resistance, we can use the same rules that we've used for other resistance type analyses. And we can go through and say, all right, I'm going to draw a resistance network. Let's say this is at EBI. I have a resistance here, and that goes to EBJ. And this is my geometric resistance from I to J. So I could write it that. This, I guess, would be Q dot I to J. So that's fine. I guess we can go through all that analysis. You use like series rules, you use parallel rules, all the same way. You can apply this to not just two surfaces. You can apply it to more. So let's go back to our three-body problem here, where we have, this is 1, 2, and 3. So I could, if I knew the temperature of each of those 3 surfaces, I could write out a resistive network, right? And that would look like, well, you have surface 1 up here, and a resistance to surface 2. You have surface 2 and a resistance to surface 3. And you also have a resistance between 1 and 3. So you have this kind of bridge, right? This Wheatstone bridge looking thing. But it's a 3-surface problem. All surfaces can interact with each other as long as they can see each other. The, I guess, difference here is that you could have heat flow going in this node. This node exists. Node 1 would be at EB1. You could have heat flow here. This would be EB2. You could have heat flow here, EB3. And then these different resistances would be what? RG1, 2. This is RG2, 3. RG1, 3. By the way, RG1, 2 is the same thing as RG2, 1. Or 1, 3, and 3, 1, right? They're the same thing. So it actually doesn't matter which way you write it. Okay, so but this is like how you'd go about setting it up. Then what we can do is, knowing that, okay, this is Q dot 3, this is Q dot 2, this is Q dot 1, I could go through and write a system of equations for each of these, where there's an energy balance for Q1. We have Q1 coming in. We have 2 paths of heat flow going out to these 2 different emissive powers. You can write a set of equations. In this case, it'd be 3 equations. And then as long as you know something about like the temperature of the surface or the geometry of the problem or whatever, you can then solve for everything you need to solve for. So let's see, what does this look like? So this is for 3 surfaces. For 4 surfaces or 5 or more, it becomes more complicated. So the way that we deal with that, just in the last minute here, would be I would conceptually say I've got some node. Let's say this is a node here. And this node is EBI. Into this node, I have Q dot I. Out of the node, I could go to any number of surfaces from, say, 1 to n. Right? You have an n surface problem. So up to surface 1, I'd have a resistance. This would be EB1. Up to surface 2, this would be EB2. Right, up here, this is RI1, RI2, so on down to RIN, EBN. So the challenge is, I guess, you're going to have an unknown emissive power, potentially, because you maybe don't know the surface temperature. You have unknown heat flow. We're going to need to use the geometry of the problem to calculate the resistances. But we're going to end up with, this is for node I, right? So this gives us n unknowns, and basically 1 equation. So we do this for all the nodes now. You have n sets of equations, but 2n unknowns. Right, so that actually ends up looking like this. So we'd say just in general form, Q dot I is equal to AI sigma. Now we have to do the summation for j equals 1 to n of Fij, so ti to the 4th minus tj to the 4th. Right, that's actually the same thing as saying ai sum j equals 1 to n Fij ebi minus ebj. And then this is going to be repeated for I in the range 1 to n. Okay, so we have 2n unknowns. Like we don't know the EBs. We don't know the Q dots. So that's 2n unknowns. And we have like n equations. So we need to basically provide a boundary, like n boundary conditions. We need to say something about the temperature at the nodes or the heat flows at the nodes. And then once we do that, we could come back and solve the problem and basically compute the EBs and then back to the temperatures. So I guess that's all the time. I have an example I'll go through at the start of next lecture that actually does this, but for now we'll leave it there.